Okay, hopefully, hello and welcome everybody. I'm Andre or Ax, and I'm a Java champion, but this is not about me. Together with me, I have Simone, who is going to give you an amazing session. I know that he has an amazing introduction included in his slides, which means I'll just disappear and go quiet, and it's all his show. Enjoy.
Thank you, Andre. So let me share my screen here. And okay. And then, is it okay? All right, so welcome to the session. The session is about a practical performance analysis, and my name is Simone. I am a Java champion too, and I work at an American company called WebTide, which is the company that provides services and support about Jetty. And so with the recent release of Jetty 12, we that now can basically run any Jakarta EE version in the same version of Jetty. So we can do E8, E9, and E10, and then in the near future also E11. We had quite a bit of work that needed to be done in order to measure the performance of Jetty 12, because we have written quite a bit of the internals of Jetty in order to support this multiple Jakarta EE environments, and therefore we needed to, have a look at how does Jetty perform. And out of this experience and out of the experience that our company has with our clients to tune their web applications and the performance of their web application that run within Jetty, this presentation came about fundamentally. So let's talk about application performance. And you've written basically your web application, and how does it perform? Well, with many answers in our field, it depends. Because the real thing is that you have to ask the right questions. And in particular, few of the questions that are interesting to find an answer for is, what is your end goal? Are you looking for application performance in order to do capacity planning? Do you want to know how many machines do I need in order to sustain the load that I'm thinking I'm going to have in production? Or can I sustain peak traffic during spikes of load, for example, Black Friday or tax season or whatever other event may happen? Or do you want to tune your application for minimal latency? Or another thing, do you want to tune your application for efficiency, meaning that you want to see if your application is efficient at using the resources? For example, does it allocate too much, or does it have too much contention on locks, and so on and so forth, right? So you need to really first ask the right question, because there's no simple answer to, does my application perform well? It's like, well, okay, it depends. So in order to figure that out, what you need to do typically is to perform a load test. And in our experience, we have identified two kinds of load test. One, we call it the steady state load test, and the other one, we call it the limit load testing. So the steady state load testing is fundamentally run at nominal resource usage, which means this is the configuration and the typical resource usage that you would expect in production. For example, you want to run your machines at no more than 50% CPU, or you want to run your network at no more than 50% capacity, and so on and so forth, right? Depends really on your application. The limit load testing instead runs until you saturate one of the resources that your application uses. So for example, you can saturate the CPU, and this is typically achieved with very small network content, very many requests per second, very little I/O, maybe just a simple request response load test, kind of load test. Or you can say, well, I want to run until saturation of the network. So for example, in this case, you want to upload big content in your request and maybe reply with big content in your responses, and you increase the request per second until you actually saturate the network. Or you can, saturate application-specific things. For example, you can have a relational database or a NoSQL database, and you want to saturate the capacity of that database. Or maybe you have a connection pool to that particular database, and you want to be able to saturate the connection pool that goes into that particular resource. Or you may want to saturate the heap memory. For example, you want to reduce the amount of maximum heap memory that you give to the Java virtual machine because you want to figure out, okay, how small can I go with my application, right? Another example is that you may have application caches that can run into saturation. For example, you apply limits to the size of those caches, and you want to say, okay, I'm going to fill my caches, and then I want to see what is the behavior of the application once those caches are full. Are they thrashing? Are they behaving properly? And so on and so forth. So both this kind of load testing are particularly interesting because they give fundamentally two different kind of answers to the questions that it may ask. Steady state is typically used for capacity planning, and as I said before, how many machines do I need? How do I scale them? What happens if we have a plan or we forecast in the future my load is going to triple, quadruple, and so on and so forth, right? How do I need to buy new hardware maybe or stuff like that? And so you do a load testing, you know what your system is doing a nominal resource consumption, and then you can say, okay, we know this number, a nominal usage. In order to sustain this other load, we need 10 machines or 20 machines or 100 or whatever. The limit load testing instead replies to other very important questions. Here's, for example, 3 of them. You will know how the system behave at its limits. So when one of the resources goes and completely saturates, you want to see, okay, so now that the system is in this condition, what do I get out of that? If I make one more request, how long do I have to wait? Or, does it get queued? Does it time out? Do I get an error or whatever? But also, if you reverse this kind of scenario, you may use limit load testing to actually find what is the minimal amount of resources that your application needs. And so you can say, okay, so if I reduce the resources, for example, the number of CPUs, you reduce the size of the heap, and so on and so forth, you can actually go all the way down to a minimum, and then you can say, okay, my application can run on this super small machine. With that configuration, I can do, for example, this many requests per second. Is that an acceptable scenario or not? Maybe it is, and therefore, by finding the minimal amount of resources, you can actually go to the cloud, for example, and choose smaller machines for which you pay less in order to sustain the load that you're expecting. Another very important question that limit load testing answers is typically, okay, so you apply a very high load for the system that is under stress, and then when you stop the load, can the system recover? That is a very important question to answer because sometimes you have your load in the real world, in production, is spiky by nature. And so can your system recover once you get a big spike and then the load goes away? Let's say the spike lasts for 30 seconds and then the load becomes again nominal. Is your system still behaving well? That may not be the case. For example, you could have had many errors. You could have, for example, small leaks that eventually turned out that your system does not behave as it was before the spike. So these are important questions to answer, and this kind of load testing is exactly what you need to do in order to answer these questions. So how do you do load testing? So we have identified in our experience 4 steps. The first step is the setup, and you need to create a load test for one of the goals that you have in mind. So if it is, for example, a steady state load test because you want to know how many requests per second do I get in order to achieve 50% CPU usage, then you write a load test that for your particular use case would be the most common in production, and you see how it goes. The typical hardware setup that we recommend is to have one server machine, and you want to have more than one loader machine as clients. And this is really important because in our experience, in particular with Jetty, what we see all the times is that the client machines are the ones that are subject to saturate way before the server does. And so because of this, you need way more than one machine on the client in order to have the server even break a sweat. Our current setup is that for Jetty, and we do this load testing automatically through Jenkins, and we publish the results via the public Jenkins instance that we have for the Jetty project. We have one server machine and we have 4 loader machines. And one additional machine that we have is what we call a probe machine, of which I'm gonna detail about this a little bit later in a following slide. So one thing that you really need to configure correctly is the operative system, because out of the box, typically the operative system is not tuned for high capacity or load testing. In particular, you want to increase the number of open files. These are the 3 common configurations that we typically find very small, that we typically need to open and change and increase in capacity. So increase the number of open files, typically both on the client and on the server. This depends on what system do you use, but if you use PAM, it's in one file. If you use systemd, it's in a slightly different file, but it's there. The other common configuration that is typically forgotten is the ephemeral port range, and this is very true on the clients. So by default, you can open a large number of connections to a server. And if you have a client, for example, our clients for the Jetty project, each client goes at 60,000 requests per second. With that particular load, you may need a lot of connections, and it may happen, and it's quite common, that the client has to open more connections than allowed by the ephemeral port range default. And so typically what you want to do is to enlarge this port range to larger values, but the point here is that you have to be aware of this configuration, because if you hit the limit, then your only choice is fundamentally to add a new client machine, because you cannot open more than, on a single server, you cannot have more than 65k connections. And so, that is something that you really want to tune on the client, and be sure that you're aware of this particular configuration in order to not get surprises. For example, a typical surprise is that the client will try to open a new connection and you get an error that says, sorry, cannot open the connection. I am out of ephemeral ports, and therefore, you get an error. And so you don't send the request that you're supposed to be sending, etc. With modern hardware, another configuration that is typically not forgotten, or in particular it is not particular taken into consideration, is the CPU governor. And you really want to set this to performance, because it may lead to surprises later, and we will see an example about this. So once you have set up the operative system, it is time to go up to the upper layer and tune the JVM. And so what you want to use is the a very recent JVM, possibly, actually, I would say very likely the same JVM that you're going to use in production. You want to set up your heap size, and you want to pick the garbage collector that it is best for your application. So this may change. But for example, I went to talk to a company, and they said, well, I asked them, who knows what is the garbage collector that you're using right now in production? And basically, everybody was looking to everybody else and was like, oh, wait a second, what is the garbage collector that is the default? And so someone replied, yeah, whatever the default is right now. I say, well, okay, but you got to be aware of the garbage collector that you're using because it may impact your performance. So if you're using Java 21 or later, I heavily recommend to use generational ZGC. It has a fantastic performances. It has a fantastic statistics report that you can find in the garbage collector logs. And, it is typically, if you have enough CPU, it is typically a good solution. It may not be a good solution if you run on very small heaps, because generational or ZGC in general cannot use compressed pointers. And so all your pointers are going to be 64 bits. And other garbage collector like Shenandoah or G1 or Parallel can work with smaller compressed pointers and therefore save you a lot of memory. So especially if you run in smaller heaps and smaller machines. The debug non-safe point option is useful to be turned on because we will see later there's an additional step that we may choose to perform where this particular option will be useful. In particular, what this does is it makes the code paths in your application more precise. And this is really useful if you want to do profiling of your application, as we will see in a few slides. So once you have configured the operating system and the JVM, what you want to do is that you want to create a load test scenario. This heavily depends on your application. You want to be able to, let's say, start. My suggestion is that start very simple. Like, for example, start with a load test scenario that just lands on the welcome page of your web application. Once you have that working and configured in your system and everything, then you can go and move to more complicated scenarios. Like, for example, I want to automate the fact that I land on the landing page of my web application, then perform a login, go to the catalog and browse the products, and then pick a specific product and then see the details of that particular product, something like that, depending heavily on the business of your application. In order to create a load test scenario, there are many tools available in the market, most of them open source or free. And for example, we use the Jetty load generator, which is written in Java, and we have a tool called the Jetty cluster orchestrator that fundamentally is able to allows you to write a load test as if it was a JUnit test. And then that piece of code gets deployed on the different machines that you have in your system. And then there is the concept of a distributed lock that can await for everybody to be ready and then start the load testing at the same time from all the client machines into the server. Similar solutions are, for example, Gatling is a similar solution. It's written in Scala. It's also clustered. Hyperfoil from Red Hat is also a solution of this kind, which is, again, very efficient because it is built from the ground up with load test in mind. It is also possible to work with Hyperfoil in a clustered way. There are cloud solutions that are specifically offered by cloud providers. So, for example, Azure or AWS allows you to say, hey, we do have a native cloud solutions for load testing your web application. You're gonna use us, and you have a somehow also your load testing within the cloud that you're using. JMeter also is a solution also written in Java that can be clustered, has agents that you can install in different machines, and then write scenarios for JMeter, and then have JMeter to actually apply the load on the server. Work2 is another good solution, is written in Chi, and so on and so forth. So it's there are tools out there. You gotta know a little bit your tools, but there's plenty of tools available already to create your own things. This is probably the thing that I'm going to remember to you the most during this presentation. The most important thing that you have to do when you write load testing is that you have to enable resource tracking. And by resource tracking, I mean whatever comes to mind that you're interested in, and even the stuff that you're not interested in, but you think it would be, interesting to know whether they're working fine or not, because these resources could be a bottleneck of your system and you don't realize. So in particular, you want to track CPU, network, SSD activity. You want to use the perf tool if you are in Linux to monitor the hardware counters. You want to use JHiccup, for example, to monitor the system hiccups. You want to turn on the GC logging. You want to monitor your threads. You want to monitor connections that your system either receives or opens to other systems. And in particular, in the web in HTTP, what you want to do is that you want to monitor responses, in particular their time, their type, whether there were errors or not. And so, this list is not complete. It may be, this is a good start, and it's typically okay, but you may want to monitor other things depending on the system you're working on. So this is the typical scenario. We have a server at the top. We have the loaders on the left. Each of the loader and the server have resource tracking enabled. And then you can have on the side another machine that we call the probe. And this machine is interesting because sometimes when you gather resource information at the loaders, you do not really get numbers that reflect what the experience that a new user coming into your system, for example, using a browser, will actually experience. This may be very different because the loaders are loaded and they are frantically trying to send requests and process responses, and maybe the rate that they're sending these requests and responses is very high. So these machines may be really taxed. On the other hand, a new user opening their browser and connecting to your system doesn't have any load imposed to it, and so the experience that it has may be totally different from that of a loader. That's why this probe machine is similar to a loader, but the load that imposes to the server is very small, so that the machine has plenty of resources to actually send requests and receive responses, and therefore it will more closely mimic whatever a new user coming into your system will see. And so the numbers out of this probe may be more interesting than the numbers that you get out of the loaders. Also, the probe should be resource tracked, of course, because you never know, what's going on in the particular machine. Especially when you're trying to do limit load testing, you want to check at the probe. Am I getting any error? What is the percentage of errors that I'm getting, and so on and so forth. Okay, once we are done with the setup, what you want to do is that you want to establish a baseline. And the idea of the baseline is that you want to run the load test, and you want to, again, start small to be sure that everything works. and then maybe make it more complex. But then what you really want is that if you run the baseline multiple times, is it reproducible? Do you get the same numbers out of it? This is really important because you may hit one lucky run, but then the second run, it may be different, vastly different, possibly, for many reasons. And so again, you want to record the resource usage during the baseline and say, okay, if I run, let's say, at 1,000 requests per second, I see the CPU this much, I see the network this much, and so on and so forth. Then you have a baseline. And then at that point on, you can say, okay, based on this data that I'm collecting here, I want to run maybe another run at different requests per second and see how the system behaves with different loads. And this brings us fundamentally to running the load tests. And again, it is a matter of running the load test and gathering the data. Again, you want to gather the data both on the clients and on the server. And by clients, I mean either the loader or the probe, but both if they are both present. And you want to gather the data on the server too. And you really want to make sure that the numbers make sense, because sometimes they totally don't. And, sometimes it's really weird. You expect certain numbers, you see maybe 10 times that, and you say, oh, okay, why the system is so fast? Or why is the system so slow if the numbers are 10 times slower, right? And so the idea is that you want to gather this number and then analyze them with, and what we suggest is to use Brendan Gregg's use methods. Use stands for utilization, saturation, and error. But typically, the way that you want to analyze your numbers is in the opposite order. So first errors, then saturation, then utilization. Only that the acronym wasn't that nice in the reverse order. Let me give you an example about this. So I remember running a load test for Jetty, and it turned out that I made a typo in the URI of the clients. And so I start the load test and immediately see beautiful numbers, like Jetty was running really, really fast, and it was, everything was working really, really well. And I say, oh, wow, this is, better than expected. But then I went and say, okay, let's analyze the number. And I say, okay, how many errors did I get? And then turned out that rather than getting out 200s out of my HTTP requests, I was getting out 404s. And 404s are typically very quick to reply. The server, is typically very fast at replying with a 404. And so the idea is that had I not looked at the errors, I would have thought, well, the system is behaving really well for the use case that I've written, and I would not have noticed this. And then when I was going to production where the typo in the URI was not present, I would see a very different performance profile, and that would have been, some scratching your head, and it's like, oh, what's going on, right? So go for that. So first, look for errors, verify, investigate errors. Then look at saturation and look for resources that could be at maximum capacity. So, for example, look for the network bandwidth capacity. Look for the CPU. Those are the typical two that you wanna monitor. But then, depending on your application, you want to monitor, for example, your caches. You want to monitor your connection pools, maybe towards database, and so on and so forth. Bear in mind that the resources may saturate even when their utilization is not 100%. And this is because the utilization is typically an average over time. So you can say, for example, oh, my CPU is at 75%. Yes, but maybe that 75% is made of a period of time where the CPU is at 100%, and then a period of time where the CPU is at 50%. And then when your system has all the CPUs at 100%, well, it cannot do more. and therefore, you may end up into a situation where you think you're just a 75% or maybe even a 50%, but it turns out that maybe for prolonged period of times your CPU are actually bottlenecked, and there's no way that you can push more even if you try, because the system has this wavy kind of load where you get a spike of load and then no load and then a spike of load and then no load and so on and so forth. And so it looks like, oh, I'm only using 75%, so I can push more, but actually, no, you cannot push more because the load that you're actually applying right now already saturates the CPU for the time that the load is applied. So after that, you look at the numbers and you say, are the numbers good? And you may be totally satisfied with that and say, okay, I have run my, let's say, steady state load test, brought the server machine, a 50% CPU, which is what I'm expecting to run in production. And I see, let's say, 10,000 requests per second. And, that's a very good number. We expect a lot less than that, so our system is fine. Maybe we can even go with a smaller system. At that point, you can ask yourself, well, can I improve the numbers, or can I run the system in a different way if the numbers are already that good? And in order to answer that question, can I improve my system? I have to know where the resources are spent, and this brings us to profiling. Profiling is, we recommend to do this profiling asynchronously based on the tools that can do asynchronous profiling. And so one of them is Async Profiler, which is the open source one and most common, but also JProfiler can have a mode where it can do async profiling. And by async profiling, what I mean is that it is able to poll and collect the stack traces independently from each other, so from each thread. And typically this is based on a private, non-public, unmaintained call into the JVM called async get call trace. However, very recently, Async Profiler with version 3, I think they have implemented an alternative way to do asynchronous thread polling to gather the stack traces, which is not based on async get call trace. And therefore, this will make their implementation more stable because they do not rely on this private, not supposed to be used call into the JVM, and therefore obtain interesting information in the same way that this call was doing, but without relying on it. Once you have an async profiler, typically what you don't want to do is you want to produce flame graphs, because looking at a flame graph is the easiest and more accurate way to identify critical code paths. Again, flame graphs are a work from Brendan Gregg, which I've already mentioned before for the use method. And you really want to check his work, especially if you are into profiling and performance in general, because it has done quite some important work on this particular field. So go check him out. Again, you want to keep monitoring all the resources, even if you look at one single flame graph, because you can look at one flame graph, for example, CPU usage. But then you want to also look at other information and say, oh, okay, why do we see this? Because, maybe you see something related to the garbage collection consuming CPU, and then you want to go and look at somewhere else and say, okay, is my application maybe allocating too much, or is the heap too small? And so you have to have a lot of different information that you can page into your brain at the same time of the flame graph, and then you want to analyze all this information together. What do you do with profiling? Well, you run typically a load test with the profiler enabled. Typically, we suggest to use a steady state run load test with the profiler enabled. the profiler will eventually, the run finishes, and then the profiler will produce information about it, typically the flame graph, and you collect also all the resources over time during the run. And then you analyze the flame graph and other resources. You identify hotspots that you want to fix. You fix them, and then you basically try again, and you run another run with the newer code and newer configuration. Produce a flame graph again, analyze again, and then rinse and repeat this process. Okay, so this is pretty much the generic part that I wanted to explain to you, and this is what we typically do with Jetty, and what we typically do with the clients that we have that use Jetty in their web application. But now let's go into something more interesting, which is 4 war stories that I wanted to report back to you that we had recently, especially with the work that we have done on the performance of Jetty 12. So first example is this one. We wanted to run a limit load test in order to see whether we could have the server, how many requests per second could the server handle. And as I said before, we have one server machine with 32 CPUs, and then we have client machines with also, I think, 32 CPUs. And so what was going on is that we had a loader that we started at 60,000 requests per second, and we had 4 of them, and then we hit the server. And then 240,000 requests per second, Jetty was not breaking a sweat. It was cool. And so we started to increment the load on the loaders until we reached 120K requests per second per loader. And at that point, there was something strange going on. And so we looked at the CPU usage on the loader, and we saw this particular report here. So as you can see, the idleness of the CPU was about 75% in almost all of them, apart of this outlier that was down at 32%. And this was a little bit weird, but you will look at the system like this one and say, well, the system has plenty CPU available. It can push a lot more than that. And, yeah, let's push more. However, when we looked at the graph of the number of requests per second, we would have expected here a flat line for each loader at 120K requests per second. However, as you can see, it's not a flat line. And this feels like sometimes the loader was, slowing down, and then in the attempt of trying to catch up with the imposed requests per second was overshooting, and then eventually after 90 seconds here, it was going down almost to 0. And that was not what we expected at all, especially given the CPU numbers that said, hey, I have plenty of CPU. So what was going on here? Well, we switched to a different thing, because as you can see, these numbers, these are not saturation numbers. These are usage numbers, like they're averaged over time. And so what was going on is that we again used the use method. As I said before, we saw no errors, no CPU saturation, no network saturation, nothing. And it was like, seemed to be okay. But then we figured out that by using another tool called TTOP, thread top, fundamentally, that there was the thread that was sending requests was spinning, and 120K requests per second, that thread was fundamentally always spinning around, right? And maybe over time pausing a little bit. So what was going on is that thread was sending a request and then sleep in order to match the request rate that we wanted to impose, and then loop around and send another request and sleep a little bit and send another request and sleep. At 120 requests per second, the sleep maybe was skipped, because the time to send a request was long enough that by the time it was finished, there was no time to sleep, because I had to start sending the next request, right? But the few times that this thread was actually sleeping, it was going into sleep, and then the operative system would say, oh, okay, so you're going to sleep, and then maybe I'm going to put it into a sleep queue, and then when you want to resume, I'm going to hit you on a different CPU. So we had this thread, the sender thread, that was basically jumping across all the CPUs, making them work a little bit, but not all of them 100%, but the thread itself was actually sleeping very rarely. And so it was basically maxed out. And so the easy solution that we for this was obviously to increase the number of sender threads in the Jerry load generator. Using 2 threads, now we had each thread had way more time to spend in sleeping, between requests that were sent. And so the thread could actually push a little bit more. And, this tool helped us to figure that out. The second example is quite interesting because it took us like 1 week to figure it out. And so Jetty 12 has a way to configure the threading configuration that you want to use when you handle requests, right? So there are 2 different ways of doing things, possibly more, but the 2 ones that we wanted to measure were one is called the typical event loop or selector thread configuration, where there is a single thread that gets woken up by an IO, a socket having data to read, and then that same thread is going to do the read, parsing the HTTP request, calling the application, processing the request, producing a response, writing the response, and then coming all the way back into the socket management to look at the next socket and then doing this work for the next socket, and so on and so forth. So this mode is nice in a way because it doesn't dispatch requests around. There's no context switch due to the fact that you are doing things in one thread and then you pack the whatever results that you have into a runnable and you give it to a different thread. And so you pay the cost of context switches, you pay the cost of cold CPU caches, and so on and so forth. The second mode was exactly this one. We get woken up by NIO. There is data to read in a socket. What we do is that we pack that socket into a runnable and then we give it to a different thread. And the other thread would do the read, the parsing of the HTTP request, the calling of the application, the writing of the response, and so on and so forth. And so we just wanted to say, okay, let's run a load test. Let's see whatever results come out, and let's see if there is any big difference between the 2 and so on. And so what we got was that one configuration was twice as fast, but not the configuration that we thought it was faster. So we thought, well, maybe for the load that we're imposing is a steady state load run, so not too much load. We expected the selector thread or selector loop or event loop mode to be slightly better because it was saving the cost of context switching. But it was not the case. It was actually twice as slow as the other one. And so here's the graphs of the request times. So horizontally, you can see time. Every bar is 1 second. And or 5 seconds actually, 5 seconds. And during those 5 seconds, the bar shows okay, all the requests that I got in these 5 seconds. We have latencies on the y-axis, and here's all of them. It's like the one that took the minimum is at the bottom, and the one that took the longest in those 5 seconds is at the top. And you can clearly see that the 2 configurations are vastly different. They have the graphs have the same scale. They're different. One of them is better because the bars are smaller and therefore the latencies are better. So what was going on here? Let's try to apply some brain here, because where is it that we take the time of processing at the server side when do we start and when do we stop? And then turns out that the place in the code where we were starting recording times for the processing of a particular request and the place where we were stopping that thing did not depend on the threading configuration at all. So it was exactly the same code, exactly run by one thread, and it should have been exactly identical. So why was one twice as slow to run exactly the same code? And so we thought at the beginning, well, maybe we're taking a different code path, which turns out to be, slower. And so we analyzed the flame graph, and no, it was exactly the same code path, and so on and so forth. So rather than guessing too much, we measured. And so we applied perfstat to our runs. And what we saw was this. Perfstat reports the CPU clock speed. And it turns out that one of the runs were going at 2.6 gigahertz, but the other run was going at 1.3 gigahertz, which is exactly half. And that explains the problem and why we were seeing those results. And so why was this happening? Because CPUs, modern CPUs, they try their best to save energy, to not become too hot, or they try to guess what is the kind of load that you're imposing to them. And so for this particular test, the test that was actually faster was using all the CPUs, all the 32 CPUs. And so the system reacted in a way where it said, well, we forgot to set the CPU governor. And so the default configuration for the CPU governor will say, okay, you're using all the CPUs, I'm going to give you more gigahertz because you're really using all of them. The second configuration, the one using the event loop, was only using 24 event loops out of the 32 cores that we had available. Therefore, 8 cores were totally unused in that system. And so the system reacted and say, oh, okay, you're only using 24 cores here. The other 8, you don't really use it, means that you don't really need me that much, right? And therefore, I'm going to throttle you down and I'm not giving you all the gigahertz that you need. And so this was a hard lesson that took us a week to figure out, to always set explicitly the CPU governor, like I said in the setup slide a while back, because otherwise you get numbers that are completely bogus and you have no idea why. So that is, hard lesson learned. So yeah, set CPU to performance. Let's go to a different example, like a more classic one, where we just ran a steady state profile run looking for optimization in the code. And so we run this load test, and we see this flame graph. So this is a typical flame graph. The towers that you see are the horizontal, the width of the tower is the percentage of CPU spent. And in vertical, you can see a stack trace fundamentally. And so the flame graph is really easy because by looking at the stack traces and by looking at how wide they are, you can see how much CPU is being spent in a particular code path. And so here, you can see that the magenta pieces here are the allocation of an I/O exception. So 10% of the time was spent in allocating I/O exceptions. So we look into the stack trace, we go exactly in that piece of code, and we say, oh, why do we do that for every request? That is not good, because this exception is not thrown, it was just used internally by the implementation. And so what we have done is that we have identified the spot in the code, we have removed the allocation of the I/O exception from the hot path, and now we see this flame graph. And when I compare the two here, you can see that the two towers here on the left are gone completely, and that each other tower is now proportionally better, in percentage is larger because those two towers are gone. So they can use the CPU saved by not having these two towers is now used by all the rest of the code. So this is as easy as this is, look at a flame graph generated by the profiling, find the hotspot, and we found so many low-hanging fruit in the Jetty code that it was very easy to fix, and they gave us a small percentage of performance every single low-hanging fruit until the point that Jetty 12 is now a really fast server. The last example that I want to share with you is a design, API design, driven by performance. So in the design of the Jetty API, we initially had this design here. We have an interface handler with a method handle that takes a request. And the goal of this interface is the following: analyze the request and tell me if you can handle that particular request. So each handler, for example, may decide, no, this request is not for me. And for example, you deploy a web application under a certain context path, right? And you receive a request that does not have that context path. What you need to do is that you need to ask that handler, hey, is this request for you? And you analyze the request, you see that the context path does not match, and so you return null as the processor saying, nope, this request is not for me. And eventually Jetty will say, well, if I have no one else to ask, I'm going to produce a 404. And so we first ask, is the request for you? If it is for you, then we return a processor, and then the processor actually had taking the request, the response, and the callback. And this was a very clean API from the design point of view, because in the moment that we were asking a handler, can you handle this request, the only object that was taken was a immutable request object. And by definition, the handler could not mess with the response or the callback or whatever. It could not add, for example, headers to the response, because there was no way. It didn't have the objects to operate on, because the design of this API was in this way. So the API had good things, mostly pros, a few cons, and we were happy with that. But at a certain point, we said, hey, okay, so how about we just collapse the two methods? We give the request, the response, and the callback, and then we return a Boolean that says whether we can handle the response. We can handle the request and the response. And so this API is less clean, I would say, than the previous one, because, of course, if I give you the response object and you modify it, but then you say, no, this request is not for me, and you return false, well, then you have operated on the response object, and that was not good. So the API was a little bit less clean. However, let's look into the performance of the two different solutions. And so what we did was actually, forked the project into a different branch, changed this important core API everywhere, and then run two different load tests with the two different branches, and let's see the performance out of it. And so here again are the graphs of the performance. You can see they look pretty much similar. On the top, you can see the processor solution, and on the bottom, you can see the Boolean solution. And then when we look at the numbers, we see that the processor solution, we had the integral. So if we go and calculate the integral of all the bars, so the area of all the bars below the yellow bars here, then we get a numbers that the P99 was 3.6, but with the Boolean we had 3.0. And likewise, the max integral was larger for the processor solution, but smaller for the Boolean solution. And then also the P99 range, we went from serving a response in 4 microseconds at the fastest, up to 20 microseconds at the slowest for P99. And these numbers went to 3 and 17 for the Boolean solution. So what we decided at that point was that like Greg Wilkins, which is the Jetty project founder, always says, well, Jetty is not really a web server. We want to be a fast web server. And so eventually we decided to use this new API based on Boolean, even if it was less clean, because this API would have given us like a non-trivial edge with respect to performance, and therefore, that was the idea. We can compromise on the engineering cost and say, okay, we provide an API which is less clear, but we have maybe good documentation, good Java docs that explain how to use it. And with that, we get better performance. And we want to go that way because, again, Jetty is not in the business of being a slow web server. We want to be a fast web server. So we went for this particular solution. So in conclusion, performance analysis of your web application is hard, but it is possible. There are tools available already, loaders, projects, profilers. You can use, all the work from Brendan Gregg about flame graphs and analysis methodologies. You can monitor your resources with a very wide variety of tools. You can use JFR, you can use perf. If you are on Linux, you can use top and plenty of tools to monitor the low-level resources on a system. Our suggestion is a 4-step approach where you do a setup step to configure your system. Then you run a baseline to guarantee that everything works as expected. Then you perform your load test runs. You gather the data and you analyze the data. And optionally, you can have a profile step where you want to improve your web application and you want to say, oh, okay, I want to find small bottlenecks. I want to see how locking is going. I want to see how location is going. I want to see how the CPU is going, and so on and so forth. And always look at these profile results with all the information that you have. You want to look at that and you say, oh, why am I spending all the CPU here? But then you look at the network usage and you see that you are saturating the network, and therefore you have to look at the flame graph with a different eye because you know that the network is saturated, and therefore you do not want to concentrate on other things before fixing the network or changing your profile, your load test to not saturate the network, because otherwise you're just looking at something from the wrong angle. You get all the results, you analyze them with the use method from Brendan Gregg, and then you have to apply the brain. You gotta, like in the CPU governor case, everything seemed to be okay, but 2 wildly different results. How is that? And so you really need to sit down, have a brainstorm session with your colleagues and say, okay, what is this? What is it possible to change in order to achieve? If I wanted to change something in order to achieve this difference, what would I change? And try to ask these tough questions, but then they pay off in the long run. So this is it for this presentation. If you have any questions, I will be happy to answer them. And thank you for listening. And I'm stop screen sharing. All right. Andre, if you want to jump in again.
I am with you all the time. I've seen your talk. Thank you very much for doing this. Clap, clap, clap. I'm not going to do that because I know computer microphones. But in terms of questions, I have bad news. I don't see any.
Okay, so greetings.
Were lively. And okay, I can see Kirk. Well, Kirk, thank you so much for joining us and for interacting.
Yes, system bound, likely stress on network. Yeah, usage of Gatling, very good here. And so are you opening? K6 is good. 3:37 a.m. suitable time to conduct experiments. So let's see, Kirk, what does it say? Can you highlight this?
This one?
Getting a recently unblocked thread back into CPU is a thread scheduling cost, which is often underestimated. Yep, that's definitely true, and sometimes they're unavoidable. Sometimes you hit the lock and you have to block, and then in order to reschedule the thread, you're going to pay a cost, and sometimes that cost is high, and it oftentimes pops up into flame graphs, CPU flame graphs, and we see this all the times. On one side, sometimes it's really good in the sense that if your system goes into a state where it says, well, I have nothing to do, therefore I'm going to put this thread to sleep, you know that the system is not particularly under stress, and maybe that's exactly where you want to have your system. Other times this is not good because you really, for example, you're contending too much on locks, and then you really do not want to do that, and so you see a high cost of rescheduling the threads in your flame graphs, and you gotta sit down and ask yourself questions, and maybe you perform a different runs and say, okay, we have seen the CPU flame graph. Can we run now the locking flame graph and see how does it look like? And by listening to a different event that you can monitor with stack traces and etc. with the sync profiler. So yeah, it's a very interesting remark. Measure, don't guess is the message. Definitely. Definitely. I mean, eventually there's going to be a moment where you say you're going to sit down and take guesses, like educated guesses, and it's like, okay, so why is the system slow? You make an hypothesis, you have data, you make an hypothesis, and then you try to verify the hypothesis. So you gotta take a guess at a certain point. But yeah, don't go and do something like, oh, I have not configured my system, I know that it can do 1,000 requests per second, therefore if I have X machines more, then it can do X more. Well, maybe it doesn't scale linearly, and so yeah, don't guess. Try it out. Maybe that's a very good thing. If it is an important system for you, you gotta spend a little bit of time and understand how your system works, because then maybe you figure out, oh, there's a bottleneck somewhere that I did not see with one machine, but I do see it with more than one machine. So there's no other way than trying to do that. So Antonio, have you found differences between virtual threads and platform threads in various tests? This is an interesting question, and the answer is, for Jetty specifically, not particularly. We have seen, we have yet to do extensive load testing related to virtual threads. We have done in the past, and we haven't seen much of a difference, slightly in favor of virtual threads, I would say, but negligible. The reasoning behind would be the following: that there are cases where, in particular with this many requests per second, we typically run our load test at 240,000 requests per second on a single server. So with this many requests per second, there are data structures that we use internally that are contended in a way, like, for example, either the thread pool if we're using normal threads, or the buffer pool, and so on and so forth. So in some cases, this small locking that we spent, it is better handled by virtual threads, because rather than a thread arriving to a lock, finding the lock to be taken, and then going into a mode where it goes down and says, okay, and I'm gonna go sleep this thread until the other thread releases the lock. Virtual thread have a more efficient way of dealing with these. So it's, as I said, the difference is really negligible. We can go on like talking about the difference between virtual threads and non-virtual threads forever, but I would like to give you like one warning here, which is the following. Do not, or make sure that when you measure a system with virtual threads and without virtual threads, you're actually comparing apples with apples. And by that, I mean the following. If you, for example, run on platform threads, the default Jetty thread pool is 200 threads. So you can have into Jetty at most 200 concurrent requests. They may be really fast, like the 5 microseconds range, but that is a limit that you can have. You cannot push more than that because you have 200 platform threads in the thread pool, and that's it. Now, what happens when you replace the front thread pool with a virtual thread pool, let's say? Okay. Well, suddenly you have no limit because threads pool are not pooled. Sorry, virtual threads are not pooled. Therefore, if you push the clients to send more requests per second, you will have into your system more virtual threads. But then at that point, you are measuring a constrained system with an unconstrained system. And chances are that the unconstrained one goes fast, yields a better result. But you're not comparing apples to apples, because the counter argument to that would have been, okay, so what if I configure the platform thread pool to be 5,000 threads now? Do I get similar numbers now? Maybe 5,000 is plenty enough for the load that you're imposing. And so in our experience, it typically is. The cost that you're paying is the cost of the memory that you have to, the native memory that you have to have in your system in order to allocate 5,000 threads. But fundamentally, a thread is a thread. If you have 16 or 32 CPUs, then having 5,000 virtual threads or 5,000 platform threads, you pay cost here and there in different places, but our experience is that they are quite comparable in terms of total throughput or any other measure of performance that you want to measure. The real important thing, as I said, is that you want to really measure the two systems in a comparable way. You don't want to artificially or practically constrain one system and then measure it against an unconstrained one and then say, oh, you see, virtual threads are faster. Well, no, that's not how it works. You got to be fair on that. And so that's really important. Twitter used to pin its production machines at top CPU speed just to avoid the CPU scaling issue, which could cause cascading of failures across services. Okay, I didn't know that, but that's interesting. So top CPU speed to avoid CPU scaling. Yeah. I mean, that's exactly what setting the governor to performance actually does. It is exactly a problem with modern CPUs. And depending on the age that you have, for me, that I've seen very old CPUs. I come from the times where one CPU was the only thing that you had, and therefore, and it was working at a fixed frequency, and then if you come with that mentality into the modern CPU world, you're just going to be mistakenly taking wrong decisions with that. So definitely, first thing to do in the setup slide is configure the operative system. Go whatever operative system you're using. If Linux is pretty simple, just go and set the CPU governor to performance all the times if you want to monitor the systems. And even in production, or depending, I mean, again, production can vary, maybe depends on your use case. Maybe you have a high load during the day, maybe zero load during the night. Maybe you still want to have some kind of CPU throttling in that case, or frequency scaling. But again, you're risking higher latency just because the system, you hit a CPU that was in a state, in a not performance state, and then it just runs slower. And if you're fine with that, well, you're consuming less power, you're consuming a little bit less CPU, and it's fine. But if you do not want to do that, well, then don't do it. Go and configure the operative system for that. Okay, Kirk doesn't that limit depend upon voluntary context switching rates, as context switch rates are not dependent on the number of threads? Are they not? Context switching rates kind of depend on the number of threads in the sense that they depend on how often a thread yields fundamentally for whatever reason, hitting a lock or doing some IO operation or whatever. So if you're always going into memory, of course that thread will never kind of yield, but then the operative system will preempt it if there are more threads than CPUs. So in that sense, the number of context switches depends on the number of threads. If you have the extreme case where you have one CPU and you have 10,000 threads, well, then the operative system have to juggle the 10,000 threads on that single core, and then the context switch rate is going to be incredibly high. If your threads are often blocking, well, that's a very good case for virtual threads, for example, because they are meant to be very efficient exactly at this use case. However, again, don't be mistaken, because the carrier thread that carries your virtual thread can be resumed on a different CPU. And therefore, what you're going to do is that, yes, maybe you're paying less cost of CPU context switching, going native to do all this work, because it is done by the virtual threads, but then you're going to be woken up, the carrier is going to be woken up into a different CPU, and you're going to pay the cost of the cold caches for that particular piece of code. This happens with platform threads as well. It's not, it's not something that is specific to virtual threads, or it happens because that's how they work. But again, virtual threads are a tool, a powerful one. They should be used with the cases for they have been designed for. So in particular, very many tasks and a lot of suspension due to stoppage, for example, IO or sleep or lock contention or stuff like that. If you have these cases, then virtual threads are a very good solution. However, as I said before, don't be fooled by the fact that now you can say, oh, okay, I'm going to throw out my thread pool at the front, just let an infinite number of threads into my system and hope that nothing happens to your system. There are very good chances that it will work really well if it doesn't pass a certain exhaustion of other resources. But if you have a system that eventually gets a really big load spike, and you do not have a system at the front to limit the number of threads that enter your system, you're going to exhaust some of the resources in your system. Let's make an example with a JDBC connection pool. If you have a JDBC connection pool that only has, let's say, 10 connections, if you allow in 200 threads, platform threads, well, then they're going to compete for these 10 connections. If you allow in 10,000 virtual threads, they're going to compete for these 10 connections to the database anyway. And now Now you have 10,000 virtual threads in, and you got to be careful of letting them in and contend exactly at that particular point, because maybe those 10,000 threads carry with them 10,000 requests, which will occupy space in the heap, and eventually you end up into an out of memory error just because you let an uncontrolled amount of virtual thread into your system, and you run into out of memory errors because of that. I mean, obviously these are extreme cases, but again, the best way to handle a system is apply some brain into it. You put there are thread pools in the front for caching threads, which are costly resources, but that's not the only reason you put them at the front. You put them at the front because your system is limited, and you somehow want to limit the number of things that can enter your system. If you can block, for example, incoming requests into the network stack so that you do not allocate a single byte into the JVM space, right? Because you do not have enough platform thread to handle additional connections. Well, that's a way to fundamentally make your system more resilient in a way, right? And then you still have to manage them, but they may time out at the client. They may get some other kind of timeout, and your system survives. It's not able to handle the load entirely, but your system may survive. If you let them in, all the connections that are coming can enter the system, no problem. We have virtual threads, allocate as many as you want. Well, then you're allocating as many as you want, and eventually your system may fail on some other resources that there's not enough of it, and doesn't matter whether you use virtual threads or not. So virtual threads are a wonderful tool, great idea, and but it's a tool. It should be used properly, and you should think about it when using it. Am I making my system now completely unconstrained? Is that a good thing or not? Well, if you have 10 requests per second and the most that you can possibly get is going to be 20, maybe it's a very good solution. Virtual threads will probably make absolutely no difference. But if you have a system where you can have maybe spikes of load that are 10 times the normal load, well, you gotta put in place some other solution that reasons about that, and then maybe again virtual threads are a very good solution for that case as well. But you gotta sit to a table and understand how your system work, and then if virtual threads are a good solution, then well, go for it. Just to say that Jerry 12, we support virtual threads for, we've been supporting virtual threads since they exited in Java 16 as an experiment. And so we've been working hard in Jerry to avoid using synchronized and pin virtual threads. And so Jerry is perfectly usable with virtual threads. And as I said, we have run load tests and we get slightly better results. So, but typically on par. So is it really worth it? Maybe yes, maybe not. It really depends on the application at this point. Sometimes you want to compare things like, oh, I've written a web application based on blocking IO APIs. Now I have two choices to make it more scalable. Either I go virtual threads and I keep the same code as before, blocking IO APIs, or I go asynchronous APIs, IO APIs, and rewrite the whole application. Well, that's a big effort. At that point, you make an engineering decision and you say, well, let's put on, the balance, pros and cons of one solution and pros and cons of the other solution, and let's see, who wins. Let's do a trade-off between the two and say, okay, we'll go for this solution because, and then it's an engineering decision and it's recorded and it's taken with a reasoning behind. So, yeah. end of the warning about virtual threads. They're not the silver bullet, like nothing in our business, in our field, and they're very useful, very interesting. Definitely consider them, but consider also what comes with them, like thread pinning and so on. So, yeah. Okay, so let's see. Oh, John Sperling, actually, and which CPU does it land on? Yes, because now we have different CPUs depending that are not the same. You can have performance cores, or you can have economy cores, or whatever they're called. Yep, definitely. So let's see. Okay, so copying the stack is required to mount a virtual thread on a carrier thread. Doesn't this affect performance? Okay, so copying the stack, I don't think it's, it might happen in some case for virtual threads, but I think I've watched a presentation from Ron saying that copying the stack may be heavily optimized. Either it is already, or it is going to be in a close future. So it is basically an implementation detail. Also, bear in mind that copying the stack may be a really fast operation. So it is very common that when you have to copy a data structure that is in consequently in memory, like it is aligned in memory one after the other, which like a stack trace could be, then for a CPU to copy that particular memory is going to be like super fast, because it prefetches everything in the front. Oh, I know that you're going to need this next cache line in memory. And so we have seen this like all the times in Jerry as well. I mean, even for cache data structure, sometimes you really want the semantic of a set or of a hash map, but you realize that if you use a list, you're so much faster, just because iterating over an array and even checking for, oh, does this object already exist, and paying the cost of the iteration is faster than actually computing the hash code and jumping here and there to find the right slot in the map and so on. So yeah, it depends. I wouldn't, again, this goes back into the mantra that I said before. Don't guess, measure. The hypothesis is copying the stack is costly. Maybe this is a benchmark that is difficult to realize, because you got to go not at the application level, but you got to go at the JVM level. But then I'm thinking that, if there is a cost for doing that, the implementation in the JVM could work on that, could optimize it. There's no need to actually maybe copy the stack. I mean, it can just be a pointer switch, and it can be done with it. So. Is there an accessible load test for virtual threads that we could use as a reference? So again, here, my take on this is similar, in the sense that it really, really, really depends on what you're doing. I can create a load test that heavily is a very good case for virtual threads. And I can create as well a load test that is heavily biased towards platform threads. And at that point, it's like, okay, what is exactly your use case? If you're talking, hey, my application is a REST service which reads JSON, parses JSON, goes to a JDBC database, performs 2 queries, and comes back and produces JSON and writes JSON. And the JSON that it reads and writes are maybe big chunks. I'm talking maybe megabytes. Well, then you have a use case. Is that virtual threads good for that? Maybe, because there are very good chances that it may block on IO, block on the connection pool towards the database on the lock, blocking the IO towards the database, and blocking the write of the JSON coming out. So maybe it's a very good case for virtual threads. Other than that, maybe you have a case where everything is cached in memory, and past the first request to populate the caches, then everything else runs out of memory. And then in that case, there's absolutely no difference between a virtual thread and a platform thread, if not, again, the memory consumption that you have at the OS level for allocating the platform thread, right? Or the many more platform threads. But from the point of view of that, is not particularly different. Another warning that I can give you is the following. Be very aware of the code and the library that you use with virtual threads. I'll give you an example. We got an issue opened to the Jerry project saying that when these people were using virtual threads, they were seeing the virtual threads be pinned, and the system was going into a complete lock. And then we asked to take a stack trace, and then the stack trace was showing that what they were doing was they were using Kotlin, and they were initializing or asking for a connection from a Kotlin companion object, which fundamentally is implemented in the library, in the standard Kotlin library, by using a synchronized block around the initialization code for the companion object. And so that was pinning the virtual thread, because the virtual thread was entering a synchronized lock and then hitting some other lock in order to create the connection or some IO operation. And at that point, the carrier was pinned. The virtual thread was pinned. And so you pin 8 of these, and if you have 8 cores, and then the system doesn't work anymore because there is no available carrier thread. They're all pinned. There's no available carrier to actually do anything else. Maybe even not one, there was one task that was unblocking the ones that were blocked. And so that task would have been put into the fork join pool of the virtual threads, waiting for a carrier to execute it, which would have unblocked another pinned virtual thread, but there were no carriers available. And so it was staying there in the pool forever. And the whole system was completely ground to a halt. And so we said, well, there's nothing that we can do. I mean, this is thread pinning and virtual thread pinning, and it's not a Jetty problem. You should avoid using synchronized. But if this is in the Kotlin library, there's not even something that you can do in your code. You have to ask the Kotlin guys to not use a synchronized block. Another example that I've seen very recently, there was a blog about a system, again, that was pinning all the virtual threads. And so their solution, quite amazingly, was the following. They went from a system with a thread pool at the front, which was allowing a number of platform threads into their system. And so there was a limit to that, right? So let's say 100 threads. I don't know what was the configuration, but let's assume 100 threads, right? So your system could go and let 100 platform thread enter the system. They switched to virtual threads, and they realized that the virtual threads were pinned. Let's assume that you have now 16 CPUs. You have 16 threads, virtual threads. They pin their carrier, and now your system is stuck. Okay, so now what was the solution for this guy? Well, we use a semaphore at the front. We still use the virtual threads, but now what is the number of permits that you want to put in that semaphore at the front? It cannot be 100 like it was before with the thread pool. It has to be the number of cores, because you do not want more than the number of cores to enter the threads, because otherwise you pin your system and it doesn't move anymore, right? So if you look at this before and after, it's like, okay, before I had 100 platform thread running through my system and be able to do work. Now you have, with a thread pool at the front, now you have something like a thread pool at the front, but it's now a semaphore, only allowing 16 threads, if that's the number of your CPUs, into the system. And that is something that you need to sit down and say, okay, did I really improve my system by moving to virtual threads? Not really. Maybe the fault is not you, but it is that of a library that still uses the synchronize and pins virtual threads without knowing even, right? And so we really need to push for library authors to do things better, especially in the context of virtual threads, and try to avoid pinning as much as possible, and so on and so forth. So this is something that we have done in the Jetty project, for example. There was a moment where we said, okay, virtual threads are coming, and therefore we need to make sure that we are not pinning any thread. And so we moved all the usages of synchronization block in the Jetty code with using locks. And so locks are now friendly to virtual threads, and we don't pin anything. So yeah, I mean, it was a huge task, touched a lot of Jetty code, kind of annoying because it's a search and replace kind of thing, but yeah, gotta be done, and we did it, and like us, many others.
I have to quote Kirk here. Great talk, love the case studies. That's the end of the quote. I will also add something from myself. Thank you for the absolutely comprehensive Q&A session. It was a pleasure to listen, and you could have had another slot, basically. Thanks, Simona.
Yeah, sorry about that. Thank you, Andre,
It was amazing. I think everybody who's still around shares the feeling. So have a great day.
Yeah, you too. Thank you for listening. Bye. Bye-bye.